Okay, and so what exactly, like, what is our, like, how does our compiler work? I didn't do,
I'm so glad you asked. So,
yeah,
okay.
explain this to me.
Okay, so typically most compilers out in the wild operate in kind of like, there's essentially 3 stages, right? And it's kind of like a rough pipeline to get from one end to the other, right? So
Yeah.
when you read the source code in, you have to parse it, which is essentially like having the program do like essentially sentence diagramming, right? You probably remember that from grade school, having to break down what the subject, the object, the verb, and so on are. We're essentially doing that when we do parsing. And so out of parsing, your aim is usually to get some kind of abstract representation of the program. And it's usually like the sentence diagram we call an abstract syntax tree because it tends to take like a tree structure to it. So for example, like a good example of this might be like a array comprehension or something, right? And you have like maybe 3 distinct like parts of what make up that expression. Those would be leaves coming off of the node for this is an array comprehension. Here's the head part. And then here's like the variable assignment, and here's the collection things are coming from. And then maybe another node for the expression for what operation's being done, right? So you have like those all fold out. But like each of those parts might be fairly complex. Like the collection you're pulling from might itself be another comprehension, where it might be like a built-in call, right? And so then you would have to add more nodes onto the tree to describe how to actually evaluate that. So then comes the next step. So the middle part of a compiler, well, okay. So I'm getting muddled down in the details. The big 3 stages are parsing, usually working with the intermediate representation, like optimizations and stuff. And then the last stage is usually, we call that stage usually code generation. OPA is weird because we can do the normal compiler flow, and then we also can do what is called interpretation. So interpretation is where you do the first stage, maybe a little bit of the second stage, but the third stage you totally skip and you instead run the abstract version of the program while it's in memory and do stuff with it. So
And
instead of like,
is that why OPA is so fast? Because we skipped the last part and we're just like running it in memory from the abstract version?
it's kind of that. So like when you load up a Python program, it's doing the same thing, right? It parses the Python code, turns it into an intermediate representation, and then runs the intermediate representation directly. And we're essentially doing that. We just don't do the same kinds of steps that like the Python guys are doing. They actually do all 3 steps, and then the last step becomes their in-memory representation, and they've like boiled it down as far as they can go, which is for them bytecode. I probably didn't do a great explanation there, but when you run an OPA program, what's happening is we parse the code, we get that abstract syntax tree, and then basically when you run a query against the module that you loaded up or whatever, you are essentially, you are picking like a spot that you are now calling like the top of the tree, and you're saying, cool, I want to know what this is, evaluate everything beneath it in the tree. And so then the evaluator, which is probably one of the most complicated parts of OPA, basically is just like a very crazy, like recursive tree shaking operation where it just goes down every leaf and then walks the results back up. Like it goes down every branch of the tree down to the leaves and like fills in the holes if necessary with like whatever came in on the input document or the data document, right? And then like once you get down to the leaves and you have actual values, then you can start shoving those up the tree and building out the higher level things. Like for our comprehension example, like every single like leaf that's attached to that makes up the parts of how you would evaluate the comprehension, you would have to actually recursively travel down, get a value to plug into each spot, right? And once you've plugged in values for all the spots, then you can evaluate the comprehension and get a value out. and then move that up the tree to whatever was using the comprehension.
Gotcha. And so did we do this like tree shaking evaluation model because this is way more performant than
I think it's
actually
mostly
compiling it? Or yeah,
well,
like what was the reason there?
Okay. So the deal with compile, I guess you could say for latency purposes, it's pretty dang good. Compiling it usually during compilation, the middle step, the one where you're working on the intermediate representation, tends to be where it's kind of like if you've done cooking before, right? Like where you sit there and you like boil the water away from something and you reduce it down for like a sauce or whatever, right? Like something is lost there, but you get a really good end result, right? You get less material at the end, but it's like it has the critical bits, right?
Yeah.
Compilation often does kind of the same thing, where you start with rich information about the program when it first comes in. And then as it moves through the middle phase where you're kind of tinkering with the intermediate representation, the compiler strips away all the unnecessary parts and leaves a reduced version down that implements just the critical logic required to make the program go. And usually when you're doing all that, the compiler takes advantage of all that rich information it has in order to know what it can safely rip out, right? And you get a much more efficient, reduced down result that, like, if you're compiling a Go program, like the type information is the rich info the compiler has that lets it generate a really efficient end result for the code gen step. Excuse me. And like with LLVM, the middle step is actually the biggest part. Like the 90, maybe not 90%, but like the majority of LLVM's code base is actually just optimization passes in the middle phase. And they just run all of these passes back to back to back to back. And they transform the program each a little bit at a time and gradually reduce it down to something that's efficient and fast. Just kind of why.
Okay.
We don't do hardly any optimization whatsoever because the representations that are easiest to do optimization passes on, we don't actually generate. Trees are hard to do optimization on. So we only do 1 or 2 optimizations that are really easy to work with if your data is structured like a tree. So like constant propagation, I think, is one of them. And then like the indexer, I think, is able to do a couple cool tricks based on that. There might be a few others. I know Stefan knows a good bit more about the actual passes we do. That's one of the things on my reading list. I got to go read how do we do that? Because there's certain things I just haven't messed with yet.
And wait, so that just reading the code base, or do we have this documented somewhere?
I don't think it's documented. So part of my motivation for gradually going through the entire code base and working with each part is so eventually I can be the guy who actually writes the document that says, okay, as of this OPA version, this is how we actually do the things in the compiler. Because I love reading that from other people for projects like Lua JIT. I loved some of the little tidbits that their compiler guys wrote up, you know, and the PyPy guys with their Python just-in-time compiler. You know, they actually talked a little bit about here's how we do this. And, you know, the GCC and LLVM folks have written volumes of text on how their stuff works because with their compilers, you kind of need it.
Yep.
So basically, like when we talk about the compiler, what we mean is the first 2 stages of a traditional compiler, right? The parsing the code, getting the in-memory version, and then we usually don't actually do all the boiling down that a normal compiler would do. We just leave the representation as it is in memory, and then where there are holes that reference outside data, when a user query comes in, and we have like an input document and a data document, that's how we plug the holes up. And when a query comes in, that directs how we recurse down the tree to find all the parts that we got to plug and then return it all back up. It sounds excessively complicated, and it might be a bit more complex than we strictly need, but there are good reasons for why it's built this way, and it's correct. It's just, I don't know. I
non-traditional.
It's a bit non-traditional. Now, the one advantage of like not doing all the normal like compiler passes to boil it down is those take time and a lot of CPU to do. You have to sit there for a hot minute to do a lot of optimization work. And if you don't do a ton of optimization work, then you have to be incredibly clever about the boiling down steps that you do choose to do. And it can be tough to get good performance if you don't do some of the expensive steps. So by just not doing any of that work at all, we actually skip having to sit there for a long time spinning our wheels doing nothing useful. So it kind of like, there's a little bit of latency budget that we're saving by just interpreting directly using the AST. In the future, if we used like a bytecode format or something, that might be more efficient, strictly speaking, because that implies that we've pre-compiled somewhere along the way, maybe at like bundle activation time. But I know that's something that like Stefan and Torin have experimented a bit with, especially around the WASM stuff. I don't know what the trade-offs have been there just yet. But yeah, so basically, if you have to explain it, like OPA parses all of the code coming in into a abstract syntax tree in memory. And then when it's time to actually evaluate a policy, it recursively walks the tree and fills in the blanks. Is essentially what's going on.
Okay, that makes sense to me.
Yeah, and like there are optimizations so that OPA can know when it can skip going down certain branches, or like if one branch succeeds, maybe you don't need to go down all the other branches, right? For like early exit and stuff. So there are definitely some optimizations that have been done by the crew, but like I know like the indexer isn't as smart as we would like it to be yet. You know, there are like some expressions it can't detect are the right pattern. And so that's like
I've seen those tickets sitting there for a couple of versions. We haven't quite done them yet.
There are reasons why we haven't done them yet. It's because it's tricky.
Okay.
But yeah, so when I talk about the compiler, it's like mostly the parser is the thing involved there, and then translating things into abstract syntax tree. That's kind of like what we refer to as the compiler.
Okay.
Yeah,
that makes sense to me now. Yeah, this definitely clarifies what I was like as I was looking. I was like, I don't think I really get this.
Yeah.
And then okay.
The evaluator is the part that does all the stuff involving traversing the tree. And so like we have, because it comes from a logic language heritage, logic languages work a lot like Rego rules, except that's the norm. So like in Prolog, you have like facts and rules, and like facts would be equivalent to like variable assignments, right? Or like,
yeah.
And then like you have like rule declarations all over the place, and they have like a couple different terms for this because math people have fun names for things. And so like in a Prolog program, you're essentially doing the equivalent of like a Rego query, but often like leaving like a blank variable that needs to be assigned. And essentially that's the norm in Prolog. Like when you want an answer to your Sudoku puzzle, you would just have that, but like with potentially a ton of variables that have to be filled in according to the constraints. So you would just have like a bunch of queries that all have to simultaneously be true or something. And you would describe like the Sudoku puzzle constraints. In theory, OPA might be able to actually solve Sudoku puzzles. I haven't tried.
Well, we did it for Wordle, so maybe Sudoku's next.
I think Sudoku could actually be a valid target. I got to think very carefully about what the solution looks like, because we don't, like Prolog will let you do some really crazy stuff, and OPA, because of the constraints that it needs to work in, we don't provide some of the same tools for good reason. Okay. But like for a lot of Prolog interpreters, they have that kind of like tree structure to things. And so that's kind of where OPA, I think, got it. That's the heritage, and so that's kind of like why it looks the way it does. It's part of why our like performance measures don't look the way a lot of people are used to, where we talk about like redos and stuff, where you have to like reevaluate like a chunk of the tree because a condition didn't hold somewhere, or you need to reevaluate it multiple times because you got to rewalk that chunk of the tree during the comprehension for like each iteration. Yeah.
Oh.
Yeah. So this is a probably, I'm hoping this is like an over 85% accurate picture of how the guts of OPA work. And as I get the rest of the details in painted, I'll eventually like actually write up a doc describing all of the stuff, hopefully with pictures.
All right. Well, we'll come back and watch this, you know, in 6 months, and we'll see how right was Philip. 85%.
Yeah. I'm hoping at least 85%.
Cool.
Yeah. Yeah, sorry to talk your ear off there. Do you want to just call it at this point because there's nobody showing up, or?
It is the end of the meeting, but
Okay.
I don't know. It was a good conversation, and so now there's at least some content for the office hours this week.
Oh goodness.
Office hours. Philip explains the OPA compiler.
Philip attempts to explain the OPA compiler.
No, 85% accuracy.
Stefan's gonna watch this and have comments. Oh my goodness.
Cool. All right, Philip. I'll talk to you later.
All right. Talk to you later.
Bye.